Today we're starting Chapter 6. This is Lecture 1, and we're looking at the periodic table. The periodic table's main contributor was Dmitri Mendeleev, who organized the elements by increasing atomic mass. His genius was that he left spaces for elements that were not yet discovered, and he predicted the properties these elements would have. So he left spaces in his table for the elements scandium, gallium, and germanium. However, he had some issues. For instance, if we look at group 16 and group 17, group 16 has the element tellurium, and group 17 has the element iodine. Tellurium's atomic mass is 127.60. However, iodine's atomic mass is 126.909. So iodine, in order to be placed in group 17, which is where it belongs because it's chemically similar to group 17, had to be switched with tellurium. It wasn't until Henry Moseley arranged the periodic table by the increasing atomic number that this then made sense. So tellurium is atomic number 52, and iodine is atomic number 53. So the increasing atomic number, or an atomic number, is the number of protons found in the nucleus. This led to the periodic law. In the periodic law, there is a repetition of chemical and physical properties of the elements when arranged by increasing atomic number. So our modern table has groups, which are vertical columns, which are chemically similar to each other. And we have periods. Periods are horizontal rows. And we're going to see this chapter that there's a repetition in properties as we go across a period from left to right. We have to know how the table is broken up. We have what are called the representative elements, which are groups 1 and 2, and 13 through 18. In the old days, they had another system where they were called 1A, 2A. You might see that occasionally in a question, but today we use just 1 through 18. The transition elements are groups 3 through 12. When we look at properties, we're not going to really deal with the transition elements, although they do follow the same patterns. We need to know the names. We did this before. Group 1 is the alkali metals, but now you're responsible for knowing these names. Group 2 is the alkaline earth metals. Group 13, 14, 15, 16 are named after the first member of the group. So group 13 is the boron family. Then we have the carbon family, the nitrogen family, the oxygen family. Group 17 are the halogens. And group 18 is the noble gases. You are responsible for knowing these names. We also need to know how the periodic table is broken up, which we've done before. Metals, almost everything left of the step except for hydrogen, and germanium, Ge, and antimony, Sb, or antimony, which are metalloids. All metals, except for mercury, which we did before, so you should look on your periodic table and find mercury, are solid at room temperatures. Metals make up about 80% of the table. Metals have luster, which means they're shiny with that metallic look. They are malleable in that they can be flattened into sheets, and they are ductile, which means they can be drawn into a wire. Nonmetals occupy the right-hand side of the periodic table. The only liquid nonmetal, you should know this, is bromine. Generally, gases are dull looking, they're brittle, and they're poor conductors of heat and electricity. And finally, we have the metalloids. They are to the right of the step. You should look to make sure you see them, but also Ge and Sb. They have certain properties that are metallic, and they can have certain properties that are non-metallic. So these are called the metalloids, and sometimes we will see the name semi-metal. Then we also did this next part before, the radioactive elements. Hopefully you have your periodic table open and you're looking. Everything higher than atomic number 83, which is bismuth, is radioactive, which means they naturally decay into other elements by releasing radiation. And we also have the transuranium series, which is higher than atomic number 92, which is uranium. These are synthesized in nuclear reactors, or we say are man-made. Following is a quick video on the periodic table, and then that will be it for today. So we'll see you later. Have a great day.
The periodic table is instantly recognizable. It's not just in every chemistry lab worldwide. It's found on t-shirts, coffee mugs, and shower curtains. But the periodic table isn't just another trendy icon. It's a massive slab of human genius, up there with the Taj Mahal, the Mona Lisa, and the ice cream sandwich. And the table's creator, Dmitri Mendeleev, is a bona fide Science Hall of Famer. But why? What's so great about him and his table? Is it because he made a comprehensive list of the known elements? Nah, you don't earn a spot in Science Valhalla just for making a list. Besides, Mendeleev was far from the first person to do that. Is it because Mendeleev arranged elements with similar properties together? Not really, that had already been done too. So what was Mendeleev's genius? Let's look at one of the first versions of the periodic table from around 1870. Here we see elements designated by their two-letter symbols arranged in a table. Check out the entry at the third column, fifth row. There's a dash there. From that unassuming placeholder springs the raw brilliance of Mendeleev. That dash is science. By putting that dash there, Dmitri was making a bold statement. He said, and I'm paraphrasing here, "Y'all haven't discovered this element yet. In the meantime, I'm going to give it a name. It's one step away from aluminum, so we'll call it Eka aluminum. Eka being Sanskrit for one. Nobody's found Eka aluminum yet, so we don't know anything about it, right? Wrong. Based on where it's located, I can tell you all about it. First of all, an atom of Eka aluminum has an atomic weight of 68, about 68 times heavier than a hydrogen atom. When Eka aluminum is isolated, you'll see it's a solid metal at room temperature. It's shiny, it conducts heat really well, it can be flattened into a sheet, stretched into a wire, but its melting point is low, like freakishly low. Oh, and a cubic centimeter of it will weigh 6 grams. Mendeleev could predict all of these things simply from where the blank spot was and his understanding of how the elements surrounding it behaved. A few years after this prediction, a French guy named Paul-Émile Lecoq de Bois-Baudran discovered a new element in ore samples and named it gallium after Gaul, the historical name for France. Gallium is one step away from aluminum on the periodic table. It's Eka aluminum. So were Mendeleev's predictions right? Gallium's atomic weight is 69.72. A cubic centimeter of it weighs 5.9 grams. It's a solid metal at room temperature, but it melts at a paltry 30 degrees Celsius, 85 degrees Fahrenheit. It melts in your mouth and in your hand. Not only did Mendeleev completely nail gallium, he predicted other elements that were unknown at the time: scandium, germanium, rhenium. The element he called ecomanganese is now called technetium. Technetium is so rare it couldn't be isolated until it was synthesized in a cyclotron in 1937, almost 70 years after Dmitri predicted its existence, 30 years after he died. Dmitri died without a Nobel Prize in 1907, but he wound up receiving a much more exclusive honor. In 1955, scientists at UC Berkeley successfully created 17 atoms of a previously undiscovered element. This element filled an empty spot in the periodic table at number 101 and was officially named Mendelevium in 1963. There have been well over 800 Nobel Prize winners, but only 15 scientists have an element named after them. So the next time you stare at a periodic table, whether it's on the wall of a university classroom or on a $5 coffee mug, Dmitri Mendeleev, the architect of the periodic table, will be staring back.